Hello, I'm Nikki LaBranch, and today I will be talking about the characterization of particulates in underground coal mines in Australia, which is the focus of my PhD. This is part of a broader strategic gap analysis of particulates that David Cliff and myself are undertaking at the Minerals Industry Safety and Health Center, aka MISHC, within the Sustainable Minerals Institute at the University of Queensland. By characterization, I mean I'm looking at the chemical composition, particle size distribution, and shape of the particles present in the respirable fraction. The respirable fraction of dust are those particles less than 10 microns in diameter, which are of particular concern because they will penetrate into the alveoli in the lungs and cause scar tissue, which can lead to coal workers' pneumoconiosis, aka CWP or black lung, and a host of other mine dust lung diseases. I'll start with a bit of history about the resurgence of CWP in Australia. Next, I'll talk about the samples that were collected and the methodology for this research. From there, I'll discuss some of the preliminary data and its significance in controlling mine dust lung diseases. For 30 years, Queensland hadn't reported a case of CWP. That is, until a retired coal miner in his 70s was diagnosed in 2015. This was just the tip of the iceberg, as Queensland started to come to the realization that it hadn't been eliminated, it just wasn't being detected and reported. The Guardian called it a perfect storm of regulatory failure, indifference from the mining industry, poor dust control, and patchy health monitoring. This led to a parliamentary inquiry into the re-identification of CWP in Queensland, which recommended a number of changes to industry. Since then, the industry and regulator have made great strides in the control of dust underground, the monitoring of worker exposure, and the health surveillance scheme. But in many cases, the damage from coal dust exposure has already been done. As of 30 September 2020, there have been 187 mine dust lung disease cases diagnosed in Queensland since 1984. The figure on the right illustrates these mine dust lung diseases as reported to Resources Safety and Health Queensland. The teal color represents the cases of coal workers' pneumoconiosis, while the black represents cases of silicosis, and the light gray are cases of COPD. As you can see, the majority of cases are not CWP. In fact, only about a third are CWP, and a growing number are silicosis and COPD. COPD stands for chronic obstructive pulmonary disease, which is an umbrella term for chronic bronchitis and emphysema. There has been a fair amount of research done on the characterization of coal in the past, but this has always relied on taking a sample of coal from the coal seam and crushing it to analyze its components. And a number of these studies complain about how hard it is to crush the coal to the desirable size fraction. And this leads to an interesting paradox. If you're having trouble crushing the coal to that size fraction, is it actually present in the mine in that size fraction? More on that later. I have been using respirable cyclone elutriators to collect the dust in the respirable fraction that exists in the ambient air of the mine. It's not just the coal seam contributing to the respirable dust. It can also be the stone roof or floor, or stone bands within the seam, the stone dusting practices, the vehicle traffic, and possibly other activities going on in the intake airway, like shoveling. In this video, you can see the collection setup on a continuous miner in a Queensland underground coal mine. The spotlight shows the dust migrating from left to right across the face towards the cyclones. The blue blinking lights are the pumps that are drawing air through the cyclones. And the square metal frames were designed to hold the pumps and cyclones in the ambient airstream. In this case, it's just in front of where the coal workers bolting the roof would stand. These are the same respirable dust sampling units that are used for compliance monitoring to measure worker exposure. I use a different filter type in the cyclone to collect the dust that can be analyzed using scanning electron microscopy. Initially, I was sending samples to the states for analysis. Professor Emily Sarver and team at Virginia Tech had started analyzing samples from underground mines in Appalachia, as 1 in 5 underground coal miners with 25 years experience there had CWP. This graph shows a comparison of the chemical composition of the respirable dust in continuous miner sections in the US versus Australia. The light blue is the carbonaceous material, which includes the carbon particles, which is both the coal dust and diesel particulates. As you can see, in many cases, very little of the coal dust is actually coal. There's a large portion of aluminosilicates in orange and some silica represented in red. The carbonates in yellow are mostly stone dust. The dark blue is mixed carbonaceous material, and there are occasionally heavy metals or other particulates present. Except for mine 3, who is cutting an area of stone in the working section, the Australian mines seem to have relatively more carbon in the samples than the US mines. This may be because Australian mines are typically leaving coal roof and coal floor. In the past year, I've been able to get these respirable airborne particulate samples analyzed in Australia. This can now be done at the UQ Julius Kruschnitt Mineral Research Center, abbreviated JKMRC, on the Mineral Liberation Analyzer, or MLA for short. The MLA is normally used to identify minerals in polished sections of drill core or lump material, and analyzing for particulates on filter is a new technique. Michelle Elms in the Geology Department has recently completed her PhD on the development of a methodology for particulates on filter using the MLA. With the MLA, I was able to identify 26 different mineral types as opposed to the 7 broader mineral categories in the US analysis. Historically, the characterization of dust in the 1980s was only able to look at the components of dust and the overall size distribution. With this technique, I can look at the individual particles for their size, shape, and chemical composition. This allows me to determine a size distribution for a particular mineral component. These samples were analyzed on the MLA. They were collected from 3 mines that are different mines and seams than the previous slide, so a direct comparison of the 2 methodologies cannot yet be made. The major trends hold the same, with relatively more carbon in the samples and just a small amount of quartz. While 26 different mineral components have been detected, I've removed the minor components for clarity of the slides, so you may notice that some don't add up to 100% now. This figure shows the particle size distribution for the carbon, aluminosilicates, and silica for mines 1, 2, and 3. These were calculated by measuring the largest dimension of each particle and assigning them to the appropriate bin, which is 0.1 microns in size. As you can see, the chemical compositions are very different. Mine 1 has a similar particle size distribution for carbon and aluminosilicates and very little silica. Mine 2 has a much larger number of smaller carbon particles than aluminosilicates, and again, very few silica particles. Mine 3 is very different in nature. For mine 3, the aluminosilicates dominate the sample, and there are also a large number of silica particles present, especially in the smaller size fraction. There's almost no coal in the sample, as illustrated by the blue carbon line on the bottom. MISHK is currently working on a gap analysis of particulates in the mineral sector, which aims to identify the current gaps in our understanding of particulates and identify areas for future research. I'm still in the process of putting together the findings from the analysis conducted so far at the coal mines, and there are plans to start sampling the metal mines as well. That concludes my presentation, and I want to thank you very much for listening. I hope this gave you an idea about the challenges we face in preventing mine dust lung diseases and why it's important to be able to characterize the dust being generated in the mines with the goal of being able to understand the variety of particulates mine workers are being exposed to. This presentation also illustrates just how different the silica content and size distribution of the silica can be in different seams. Thank you.